Jackpot.
Hey, what about the guy we're after?
Let's see. Adler.
I'm at the door, Case.
Most of us play video games every day during our free time, either on our desktops or laptops. But have you ever wondered how your computer renders such visuals? This work lies on the GPU. Welcome to Circuits and Crank, where we explore the technology behind computers, electronics, supercars, and aircraft. In today's video, we'll be diving into another essential component of a computer, the GPU. Every image you see on your screen, every movement in a game, every video frame, is not just displayed, it is calculated, built, and rendered in real time. And the component responsible for all of that is the GPU. But here's the real question: how does a GPU actually create what you see? Let's break it down from the ground up. What a GPU really is. GPU stands for Graphics Processing Unit, but that name alone doesn't explain much. A GPU is a processor specifically designed to handle massively parallel mathematical operations, especially those needed to generate images. Here's the key difference. A CPU is optimized for low latency, gives doing a few tasks very quickly. A GPU is optimized for high throughput, gives doing thousands of tasks at the same time. In graphics, every pixel, every color, every shadow is a calculation. So instead of processing one pixel at a time, the GPU processes millions of pixels simultaneously. Evolution of GPU. In early computers, graphics weren't even handled by GPUs. The CPU did everything, which made graphics extremely limited. Then came dedicated graphics hardware. Early systems were simple frame buffers just storing images. In the 1990s came the introduction of 2D accelerators. Then in 1999, NVIDIA released the GeForce 256, the first true GPU. That was a turning point. It introduced hardware-based transform and lighting calculations, meaning the GPU could now handle 3D graphics independently. From there, in the 2000s, we had programmable shaders. Developers gained control. In 2010s, GPUs were used for scientific computing. Today, GPUs power AI, simulations, and real-time ray tracing. Modern GPUs from NVIDIA and AMD now contain thousands of cores. How GPU renders an image. Let's break down what happens when a GPU renders a frame. Step 1. Geometry processing. Objects are made of vertices, points in 3D space. The GPU calculates their positions. Step 2. Rasterization. Converts 3D shapes into pixels on your screen. Step 3. Fragment processing. Determines color, lighting, and texture for each pixel. Step 4. Output. Final image is sent to your display. This entire process happens dozens or even hundreds of times per second. Frame rate. Frame rate, measured in frames per second FPS, is not just about smoothness, it's about how frequently new visual information is generated. Let's break it properly. 30 FPS gives a new frame every 33 milliseconds. 60 FPS gives a new frame every 16.7 milliseconds. 120 FPS gives a new frame every 8.3 milliseconds. Lower frame times equals faster updates, which results in smoother motion. But here's the deeper part. If your GPU cannot render a frame fast enough, you get frame drops, stuttering, and input lag. So FPS is directly tied to GPU processing speed. Resolution. Resolution is not just quality, it's workload. It represents the total number of pixels the GPU must calculate per frame. For example, 1920 by 1080 equals approximately 2 million pixels. 3840 by 2160 for K equals approximately 8 million pixels. That's 4 times more work per frame. Now combine that with FPS. 60 FPS at 1080p gives approximately 120 million pixels per second. 60 FPS at 4K gives approximately 480 million pixels per second. That's why higher resolution demands much more GPU power. VRAM. VRAM Video Random Access Memory is the GPU's dedicated memory, but it doesn't just store images. It stores frame buffers, textures, depth maps, shaders. Think of VRAM as a workspace for rendering. If VRAM is insufficient, textures get downgraded. Performance drops, stuttering occurs. VRAM is not about speed alone, it's about capacity to handle complex scenes. HDMI versus VGA. VGA stands for Video Graphics Array. VGA transmits analog signals, meaning electrical signals represent image data continuously. This leads to signal degradation, lower clarity, and interference. HDMI stands for High Definition Multimedia Interface. HDMI, on the other hand, uses digital signals. Exact pixel data, no signal loss, supports high bandwidth. GPUs output HDMI because modern graphics require precise high-speed digital transmission. GPU versus CPU. Final clarity. CPU has few powerful cores and does logic and decisions, while the GPU has thousands of smaller cores and does parallel math. That's why CPU runs the system and GPU builds what you see. So now you understand GPUs at a deeper level. They don't just show graphics. They compute, transform, and render every frame in real time. And the moment you increase resolution or FPS, you're increasing the workload on the GPU dramatically. Thank you for watching.